I think I'm going to start. It is 3:30. I just want to say welcome to everybody on this call and on this webinar. It is really interesting to see the many faces in the many places. One of the reasons why I will be presenting in English this afternoon is we've got a lot of Zambian friends of ours, farmers farming in Zambia that dialed in. Now, today's webinar originally started off as a webinar for them, and we thought, why lose the opportunity just to brush up on some of the concepts that a lot of you are already familiar with. It might be old news to a lot of you, but no harm doing just a little brush up. Also on this call, and I'm very glad there are some of our admin and support colleagues of ours at Villa also on this call, and I really hope you find it interesting that we have to share it with you today. There's around 120 delegates that have indicated that they will join us, so very good interest. I think it's important topics that we are talking about. My co-presenter, Dr. Brian de Villiers, unfortunately cannot be here today. We are busy with a series of 3 webinars around adjuvants and application technology and the importance of that. So Dr. Brian, he will be in the next session, do the adjuvants and all the things that are important for what's happening in the tank mix, as well as on the target. And today I will be talking what happens to that spray droplet, that expensive chemistry that you are trying to get onto target. And I really hope you will find it insightful. This is my part. I do want to mention, and there on the screen is Dr. Marius Ras. Some of you do know him. Dr. Marius Ras did his PhD on application technology. And I mean, he has authored thick manuals on application technology, way more detail than I can share with you today. And Marius Ras, Dr. Marius Ras is an independent consultant, but go and look him up, Ras Consult. And if you are in doubt or need some technical assistance, in-depth assistance, we will definitely be available at Dr. Marius Ras as well. We are going to talk today very broad. Unfortunately, we do not have enough time to really immerse ourselves into this subject. There's a lot of detail that we can still add, but unfortunately, time doesn't allow this for us. There might be some interesting parties, some delegates that are looking for information on orchard application. This one is a very much generic application, maybe a bit more lenient towards ground application, but some of the principles are exactly the same. And in future, we will do a dedicated orchard application session and everything that goes around with that. That said, let us start off. Adjuvants in the tank, in the air, and on the target. Today, we're talking about what happens, as I said, to that expensive chemistry in the air, between the nozzle, and before it hits the target. Maybe for some new people, just a little bit of reference from where Villa Crop Protection comes from. Villa Crop Protection currently is owned by Land O'Lakes. Land O'Lakes is a Fortune 200 company in the US. And I say company, it's actually a co-op, and it consists of 320 dairy farmers. Started in 1921, so going on 105 years already. Land O'Lakes have 3 business units. First is Perina, and that's the animal feed one. Then Winfield United, which are the ag inputs and services, and this is where Villa Crop Protection resides in. Within that business unit, there are also a Canadian business unit, a Mexican business unit, and a Brazilian business unit. And then there's the dairy products Land O'Lakes unit within the bigger holding company. Now, Villa started off in 1989, and maybe there's quite a few of you that haven't even been born yet. And this was the date of birth of this whole company until where we are today. It got its name, maybe it's christening, I don't know, in 1998 as Villa Crop Protection. And there you can see the old logo and fond memories around that. And yeah, today, well, not today, 2015 was a big mark, a big event in Villa's evolution and in Villa's growth. Land O'Lakes became the majority shareholder in 2015. So going on 11 years already. Lots of other highlights on this timeline that we didn't include, just a little bit of context of who and where Villa is. Villa's been here a long, long time. Over 600 product registrations. We are the biggest, largest holder of product registrations in South Africa. Annually, we do around 900 plus research and development trials. And these are statistical, replicated research and development trials. These are not the look-sees and the demos and that kind of trials. So we invest heavily in these trials, research and development. The Villa unit within Winfield United, around 190 employees. We have various other units, business units in the bigger Winfield holding company. One of them are Mythos, and you can see down here, we are already over 500 weather stations within that business of Mythos. Our ambitions are big. The ambitions are to have a weather station and start building weather history or climate history on each and every farm. That's our ambition with that business. Our manufacturing capabilities, 6 million liters per annum, is our capability to formulate locally in Olifantsfontein, here in Joburg, between Johannesburg and Pretoria. And we can handle 12 million imported products every year. So quite the capacity and heavily invested to make sure that there's enough products and that the quality is there. Let's get to what we are here today. Application risk. Application risk has many factors. Some of them you have control over. A lot of them you do not have control over. Temperature and humidity, yes, you can maybe manage it to an extent. But yeah, if it's too hot or it starts raining, whatever, this is stuff that we cannot control. Wind speed, wind direction, the landscape, these are all variables that are difficult to manage. Closer things that are manageable would be the travel speed, making sure that your release heights are within the specifications, nozzle spacing, type of nozzle, pressure pump, the servicing of your pump, the calibration. All of those things are things that you have control over. And it is very important that this is the basis and the foundation of mitigating risk during application. Get that right. So many times I see growers, they invest heavily in the planters and all kinds of other equipment. And yeah, the sprayer gets pulled out 2 or 3 times a season. It looks like a chicken coop, and they do not really care about that. It's an important part of farming successfully. So there are many factors that we need to mitigate. Let's start with a couple of basics again. Once again, there might be some people that find this information new to them. Here on the left-hand side is, and I'm going to use the manufacturer T-Jet as examples. There are many other manufacturers, but I think T-Jet as a nozzle manufacturer is relatively well known. Here's a yellow nozzle, and there it's got the designation XR. That stands for extended range. And then there's a code here, 11002VP. That 110 is the degrees of the spray pattern. You might get an 80, which has a narrower spray pattern. And the 02 tells you it delivers 0.02 US gallons per minute at 43.2 psi, which is roughly around 3 bar. That's the spec. This VP only stands for the type of material that this is manufactured on. So there's an 02, 110 02, 0.02 gallons per minute delivery. You get a blue one, probably see a lot of them still on places. That's the XR, the extended range, 110 03 for 0.03 gallons, US gallons per minute. And then the red one, that's 110 04, delivering 0.04 gallons per minute at around 3 bar. VP, that's kind of material it's manufactured. You see a VK and a VS, probably for that stainless steel little tip in there. These tips are original, old technology. I doubt if there are some of these on booms and on sprayers anymore. If there are, get rid of them. Most definitely. I'm going to show you what these old ones are costing. Sometimes I do get to places and you see all kinds of colors. It looks like a Christmas tree. And, oh man, then they wonder why we're not getting efficacy on application. There was a technological improvement on these older ones many years ago, and that is called the air induction nozzle. I'm going to go to the next screen. Use this one. Here's the old XRs, 110.04, and you can see on the AIXR, the AIXR 110.04, it's got a much longer body. The reason for that is this orifice over here. That acts as a Venturi system. As the spray comes out of the nozzle, it sucks in air. It gets mixed inside this chamber with the spray mix, and you get a more homogeneous sized droplet that are coming out. And I'm going to physically show you the data difference between the old XR as well as the AIXR. Now, the air induction technology is applicable to many other nozzle types. You've got the TTs, the twin turbos, lots of different ones. This larger body indicates that there is a chamber for mixing the air, just homogenizing the droplet size. The technology is the same despite the amount of orifices on top, like when you get a twin turbo or whatever. Delivery is exactly the same. It's a 0.4. There's a concept that I would like to share with you, which creates some confusion, especially if you go and have a look at nozzle selection. When you start looking at the calibration of your sprayer, deciding on what type of nozzle you need, all of them are designated with a VMD. That's the volume mean diameter. Now, the volume mean diameter is not the average size of the droplet. And I'm going to show you exactly why that is not the case. If we take this spray pattern and we can literally freeze it in time, take each and every drop and then pack them out from small all the way to large, and get that spectrum of droplets. We take then two empty containers of equal volume, and then we start filling from the small one into the first container, and we start filling all the way the first container. Remember, equal volume. We fill them up all the way to there. As soon as that first container, 2 liters, is full, the next droplet in the row that needs to go in there, that is your VMD, the volume mean diameter. And as you can see with this picture, way less droplets go into the second equal volume container than in the first. And that's why I say it is not the average size, it's the volume mean diameter that is involved there. So the first 50% of your spray volume might have X amount, mostly the biggest amount of droplets because of size, and the second 50% volume of your spray pattern might have less droplets because they are simply bigger. All right, there's, for instance, in this case, just as an example, 300 micron droplet would be the VMD of this nozzle that created this spray pattern. You need data to understand what happens with droplets. With our colleagues in the USA, we have access to the Innovation Center in Minnesota, there in River Falls in Minnesota. I've had the privilege to have visited this facility quite a few times, and every time I'm so impressed when I get there to be able to see the technology and the resources that our colleagues have. And out of this place, there's come a lot of data and insights to what happens with spray patterns. Inside the Innovation Center, amongst a lot of other things that they are doing there, is this spray analytical system. You can see there at the top of stuff, and here's a chamber. So what we do in this spray analytical system, in this spray analysis system, we can simulate different environmental conditions. Low humidity, high temperature, wind, whatever we want to simulate, we can simulate in this chamber. We can take a nozzle and simulate nozzles on for aerial application or land application. Take different nozzles, have a look at what their performance are, how does their droplet spectrum look like, and then more importantly, we add chemistry to these nozzles to see what the influence is on droplet size. It is important to understand that when you decide on a nozzle and the type of VMD that you are looking for, that calibration, or rather that designation of that nozzle, is with water. That technical spec is with water. None of us spray water. The moment that you put chemistry in, it changes that whole spectrum of a droplet. Some chemistry, herbicides, insecticides, fungicides, PGRs, doesn't matter. It depends on the type of formulation, be it the EC, SL, SC. All of them have a different influence on the droplet and on the droplet size. Some build droplets bigger, some build droplets smaller, collapsed droplets smaller. Now, one of the most well-known active ingredients in agriculture is glyphosate, obviously glyphosate. And interesting enough, glyphosate is one of those formulations, an SL formulation, that actually makes droplets smaller. I'm going to run through some numbers, and yeah, just bear with me. There's a couple of busy graphs, but we're going to get to some nicer pictures. If I take the label, I talked about glyphosate as a reference, as an example. This screenshot comes from a very well-known glyphosate supplier, glyphosate products, and on the label it says, droplet size. A droplet spectrum with a VMD of 300 to 400 microns is recommended. So keep that in mind. 300 to 400 microns is recommended. Limits the production of fine droplets less than 150 microns, high drift and evaporation potential, to a minimum. This 150 microns, the EPA, the Environmental Protection Agency, has designated that size of a droplet as high drift with evaporation potential. It is a risky size. The EU has a smaller one. I think they're around 120 or 125 micron. They deem as high drift potential, or evaporation potential is high. All right. Remember that 150. This is on the label of one of the glyphosate suppliers. We took this yucky blue one for the moment. Let's take this one as an example. We put it in the sprayer system, in the spray analytical system. And there it is. It's an XR 110.03. We pushed it to the spec of 43.5 psi, roughly around 3 bars of pressure. We added Roundup Powermax in this instance. And we had a look at what's going to happen with the spray pattern. Here is the spray pattern. There it goes from small droplets. This is the size of the droplets on this axis, and this is the density / amount of droplets in that spectrum coming out of that nozzle. Here it goes. You see this bell curve. The VMD for this one is 174 microns. There we draw in that line. All right, that's the VMD. Let's go and have a look at the 150 micron lines, that red line over there. If you go and have a look at this spray pattern, that surface area on this bell curve amounts to 47% of the spray volume. That is, according to that label, 47% is risk-sized droplets coming out of this one. Guys, this is on the actual pressure. We hope we take it for granted that the pump is fine, nobody's overpressuring. Imagine your operator is increasing pressure or whatever. This is ideal circumstances according to calibration. Now there's another line here, 105. 105 micron. 105 micron droplet is designated as never going to be able to hit target. It is too small. It gets suspended in the atmosphere, and the evaporation rate is just too high. If we draw the 105 micron line in on this graph, that surface area over there would amount to 20%. So with this nozzle, and I really hope there are nobody's still going with an 03 nozzle applying anything. This is not the self-propelled ones. They definitely have bigger nozzles, 07, 08, 09s even, and are running way higher pressures for that particular nozzles. But I really hope there's nobody using this anymore. If you look at this graph with that nozzle, 47% of your spray pattern here is under risk. 20% is not going to find its target. 2 liters of glyphosate, and you take 20% away there. That's like 400 milliliters that you take away. You can physically throw away 400 milliliters concentrated glyphosate because of this pattern. It's not going to go where it needs to go. All right. So yeah, 20% wasted. Let's go to another graph and a bit more visual on this. I'm bringing in that better nozzle, and I'm skipping straight to the 110.04 in this comparison. This is high-speed photography, also coming out of the spray analytical system at the Innovation Center. And if you go and have a look at that video on top, you can see there, that's a driftable. So that's 150 microns and going smaller over there, drifting away. While it's hanging around, it's evaporating. If it evaporates to around 100 to 50 to 100 microns, if it hits a warm surface like a leaf or whatever, then it's going to instantly evaporate. So definitely not a good spray pattern. There you can see it. I'm going to show you some other high-speed photography on this as well. Go and have a look at a good nozzle spec, the 110.04, here down at the bottom. So much less drift, way less small particles, but they still are there. All right. So equipment can take you only that far. Just the comparison between these two. To demonstrate some other factors that we learned out of this big wind tunnel, the spray analytical system. And my apologies for this this busy slide. It's kind of a photo, so I couldn't hide some of the stuff. Anyway, just bear with me. I'm going to take you here from the side. We take that same nozzle, that 110.03. We plugged it in. We created 29 degrees Celsius, 80% relative humidity, and generated a 16 kilometer per hour wind in that wind tunnel. I don't know about the Zambian guys. I know it's hot up there. Places where I come from, I'm from the Western Transvaal, Potchefstroom, going Delray and Schweizer. 29 with 80% relative humidity. I don't know when that happens. That's this ideal circumstances. 9 o'clock in the morning, we're running 20% humidity, 35 plus, and even down in the Cape, there on the West Coast, a lot of places down in the Cape, very, very hot, quickly very dry. So this is nice, ideal circumstances. What do we see out of this? 29 degrees Celsius, 80% relative humidity, 16 kilometer hour per wind. If we put the boom at 45 centimeters above the target, I've seen some labels talk about 50 centimeters above target. If we put it 45 centimeters above target and we measure the 200 and the 300 micron droplet sizes, we find that it takes 29 seconds for it to evaporate to around 150 microns and less. This 63 centimeters is the terminal velocity, the distance to terminal velocity. Terminal velocity meaning that droplets coming out of that nozzle is directional with intent, with momentum. After 63 centimeters, it has lost terminal velocity and it is there. Environmental conditions start having a big influence on what happens with this droplet. Remember, with 45 centimeters above the canopy with that nozzle, 63 centimeters terminal velocity. That means around 22 centimeters canopy penetration where terminal velocity stops. I am comfortable with that. Not too much of a problem. If you go and look at the 150 micron, remember that's that red line. It takes 12 seconds for that 150 micron to evaporate under that 105 limit. Its terminal velocity is 43 centimeters. We're doing 45. At 43 centimeters, 2 centimeters above the canopy, terminal velocity is gone. All funny things start happening, like drift. 1.4 meters, it starts drifting. And while it's drifting, remember, the environment's having that influence on it. It's evaporating, it's blowing all over the place. Now, I'm going to come back to the drift. Let's go and have a look at that 100 micron size droplet. 7 seconds for it to lose its size, going up to 50 microns. This is suspension, guys. The atmosphere is starting to suspend this droplet between 100 and 50 micron. Its terminal velocity is 22 centimeters. That's halfway to the top of the canopy. The drift on this 100 micron is 5.3 meters off target. Remember, that's movement of 5.3 meters within a 45 centimeter band. That's a lot of drift going sideways. The 150 micron is 1.4 meter. I've got the guys and they tell me, at least it's landing on the next row. It might land there, but what happens if you are spraying a contact product? Let's say bromoxynil or a paraquat or glufosinate or something like that. It doesn't go down to deeper canopy penetration. All right, so guy says, no, don't worry, I'm not too worried about it. I'm spraying a systemic product. All right, is that product systemic upwards? Because if that lands on the top of the canopy, it's not going down. Or if you are lucky, it might go down. But what happens if I've got 2-3 types of products, an insecticide, a fungicide, and maybe a post-emergence herbicide in this whole mix? Different formulations and different modes of action, upward systemic, downward systemic contact. If you don't get good coverage, top to bottom in the canopy, you are not winning or achieving what you are trying to do. There's a lot of money going lost in this 45 centimeters due to a bad nozzle selection. And I want to bring back to equipment of bad equipment. That's what we saw on this picture. I'm going to show you this short video. Unfortunately, with the trial that we did was with the 11002s, the AIXR 11002 and the 110XR 1 year. This is one that I was physically present and that we did up in the Northern Cape, there in that irrigation areas, Urania. And what we did on this side of the boom, we put this AIXR nozzles, and on that part of the boom, we left that the 110 XRs in it. And we wanted to show the farmer what's the difference is by just changing your nozzle. You will see, look at these lines in the sand that I drew. There's another one. You'll see it when I start the video just now. That is what I call the wet footprint under the boom. And you'll see on the XR, there's a way bigger wet footprint created under the boom than this one. Remember, delivery is the same. It's an O2, it's an O2. Delivery is the same. So this is drift. This is small particles going off target. And when this spray dries, you can always see it drying from here. Why? The smaller ones drifted the furthest, and they are the first one to start evaporating on this. All right, let's have a look here. You can see that spray traveling there. You can just see it there. And I mean, this is powerful. This is powerful to go and show somebody what is happening. There is no penetration, canopy penetration on this side. Here, you are getting depth penetration. Just going to show it again. Maybe there's some guys on cell phones looking at this. There you can clearly see what's happening there. All right. And then you're wondering, why am I not getting efficacy? Look at that boom height. Yeah, interesting. Look at that boom height and the difference in that wet footprint just on that boom height. Right, herbicide alone, you're getting around 20%. If you have a good nozzle, in this case, screw out that one, put in this one on the smaller sprayers, you get a 4.3% driftables versus a 20% driftables. Just some high-speed photography. I'm just going to run quickly through these. It's a bit of a repeat. It's always nice for me to visually see this. All right, this is a busy graph. I'm going to skip this one, and 2-3 slides on, we're going to revisit this one. It's just to show again the XR, Roundup Power Max, 20% driftables. AIXR, Roundup Power Max, 4.3% driftables. There it is. I'm going to come back to this graph later. So we have physically just quickly touched on just nozzles. We take it that your equipment is up to standard, you understand what needs to be done with nozzle selection, all of that is right. How do we mitigate the factors that we do not have control over, which is the formulations that go in, the time of day that we are applying, those environmental conditions that I spoke about? This is where adjuvants start playing a role after you have looked at your equipment. Now, the adjuvant in this space, that's between the nozzle and the target, is drift and deposition agents. Now, everybody are familiar with them. They've been around since forever. But there are different categories of them, and there are newer technologies. The older technologies were the guars and the polyacrylamides, and these and the lecithins even down here. They were in essence just viscosity increases. And if you didn't get your dosage right, you would have a sticky, snotty stuff coming out of the sprayer nozzles. Dosage dependent. They are not very mixable with certain formulations, especially with some of the more refined formulations that we require today. A lot of the old nasty, hard and nasty chemistry that we used to use in the formulations help to mitigate these products. These old technology products help mitigate their compatibility and their efficacy. Xylene and there's a lot of these stuff in the formulations that we do not use anymore. So guar, polyacrylamides, lecithins, they are old technologies. Viscosity increases, thickeners. The inverted emulsions were the next generation of better constructed, better formulated drift and deposition agents. Good performance. The inverted emulsions, finicky, also depending on what type of chemistry you use, but relatively easy to use if you understand which needs to go where, and performance-wise, did very good. Now, the sweet spot between the inverted emulsions are the oil emulsions. And in this case, and this is the product that we brought from the USA about 10 years ago, is Interlock, and it is an oil emulsion. It consists of 2 veg oils, but what makes it unique is the 2 oils blending is very particular, and the chain length of those 2 oils is very important. Sourcing the source of those oils, those veg oils, was a few years battle for the University of Minnesota, which holds the patent on Interlock, for them to be able to find the right chain length of both these oils so that they can be combined. It's easy to put 2 oils together, but how do they perform when they are sheared, when they are stressed within pumping systems, going through nozzles? What's that shear factor breaking this emulsion? Everybody knows how to make mayonnaise. It's easy to make mayonnaise out of an oil emulsion. So preventing making mayonnaise out of oil emulsions is a challenge. And then how does this go with chemistry? And how does this go with chemistry different than the inverted emulsions, lecithins, or the guars? One of the patented attributes of Interlock, specifically of the oil emulsions, are that it builds In the spray pattern, it builds small droplets bigger without making big droplets already in the system, already in the spray pattern, also bigger. So it tightens up that small tail in that graph. If you go and have a look at that graph on the left-hand side, those smalls, it tucks it in closer to the VMD without moving the bell curve in total or the right leg of that bell curve. And this is where the patented technology lies with Interlock. And I'm going to prove it with the data from that spray analytical system. So Interlock and this oil emulsion brings better deposition, decreases the drift, and the effect is deeper depth penetration in the canopy. Here's that busy graph. It's got some other stuff here on it as well. Sorry for repeating myself. Let's take it from the top. Here's that XR 110.03. That's the one. That's how it looks like. If we take and we add Interlock to that bad, not good nozzle, you can see it already cleans it up very, very well. Still driftables there. Let's go and look at the numbers. I marked that one gold. It is this one going up there. Where's my red thingy? There it is. Yes, 105. That surface area constitutes 20%. Adding Interlock, there it is. It brings it down to 9.5. That's how 9.5 driftables looks like. It's on the green one. Here it is, 105. That area there is 9.5. Let's take a good nozzle, the AIXR. There it is. Put it around our Power Max. You can see way better pattern than the XR. That's the magenta one. Here it goes. Surface area over there, 4.3. Cleaning up the spray pattern with Interlock. There it is. You can see it over there. There's my pointer. And that is this blue one coming to only 1.3% driftables on the spray pattern. Now I mentioned it takes small droplets and make it bigger without making big droplets bigger. We don't want to shift this bell curve that way on the spectrum. That's what the guars and those thickeners do. But have a look here. If take that gold one over here. There's my pointer now. So I lost my pointer just a moment. There it is. You can see it started off here, and that green line, the one with the Interlock, they all started off on these smalls. There they go, there they go, there they go. Look here. They both land on the bigger ones. So this is without the Interlock on that bad nozzle, and this is with the Interlock on that bad nozzle. But your smalls are less with the Interlock. And the same for the AIXR. Here it is, landing there, starting off very similar, less there from the 105, but landing very similar on this, the large droplet spectrum. And this is what is unique about this particular adjuvant that we are using. Right, let me just run that quickly for somebody to go and see. I'm just going to run it there for 2-3 seconds. All right, this is very powerful to see these variations and these differences when you're on the farm, and I'm on the farm and physically showing on your boom sprayer or whatever how that physically looks like. And I hope we can get the opportunity to do that soon. I'm especially talking to the Zambian guys on the call. I'm flying out to you guys on Monday, and we'll be visiting up in the north. I'm not going to be able to visit everybody, but hope to be working my way through there with the team in the near future. XR nozzle, just the high-speed one there again. XR plus Interlock, air induction one with Interlock. You've seen this. Yeah, visually very strong. Got to skip that one. This is a nice, interesting demo that we did the one day at one of our farmer days. Disclaimer: this picture, this is stock footage. This is not one of our guys, but the principle is the same. What we did, backpack sprayer, these electric backpack sprayers. So on that lance, it's an extended lance with a manifold. We put on the old XR nozzles, 2 XR nozzles on that side, and the AIXR nozzles on that side. And what we did is 50 centimeters above the canopy, we hanged a little string there just so that you've got your eye in on where to touch, to keep that distance. Don't create a boom swing, because you don't want variability on this. And then we put on the top of the canopy, we put water sensitive papers around 50 centimeters, and then 80 centimeters from the boom inside the canopy, we put down some more water sensitive papers. And we had a look at how does the water sensitive papers look under these circumstances with the AIXR, and how do they look with the XRs. All right, here we go. Collected the papers, the water sensitive papers, 50 centimeters, 110.04. The first run, just water. We want to see just how these nozzles perform just with water. Right, let's go and have a look at the XR, top of the canopy. That doesn't look like bad coverage. I've seen guys measure deposition with their cell phone screens, just swipe it under the sprayer, and yeah, it pretty much looks like that. I think if you use your imagination and you say, yeah, that's probably 30, 40 droplets per square centimeter, like some of the labels say, pretty good coverage, I would say, if I don't have another comparison. So yeah, just for the moment, have a look at that one. I would say not too bad. 80 centimeters. Let's go and have a look at the depth, the penetration, how much got there. Look at that paper. Look at that paper very well. You will see there is definitely less deposition than on the top. Relatively good surface coverage, relatively good. It's all over the place, not blotchy or anything. But I don't know. I would say double digits, less coverage, 80 centimeters deep. That's 30 centimeters from the top to the bottom on that XR. Right, good nozzle on the same boom, right next to it. Now things starts to poke you in the eye. That's the AIXR. Plain water, no additives yet, 50 centimeters. Let's go and look at 80 centimeters. Good coverage, good coverage. Even on the 80 centimeters, way better than 50 on the XR. All right, now we've done that run with water. Stop, fill it up, put in some interlock, run it back again. Same sequence, same thing. Definitely better coverage, better droplet deposition with the XR, with the interlock than without. 80 centimeters, canopy penetration, definitely better than there. All right, good nozzle in this case, the better choice. Wow. You didn't know what you didn't know. The moment you do this kind of comparison, you really see the difference between good deposition, bad deposition. He starts answering questions on why am I suckling, why am I battling to control my target? Why are we developing resistance? Because we are underdosing. And this was quite a poke in the eye. And I hope maybe get an opportunity to physically redo this at a farmer day if we meet up in future. Very powerful, very powerful. So something similar. We usually do not have an issue to hit the canopy on top. This is aero application, an example of how most aero applications look like. Coverage on the top, not a problem. Coverage in the middle, start losing it. And the bottom, not good coverage. Imagine the aerial application that you do here is for something like red spider mite in your corn. And the contractor, the air tractor is only coming around 11 o'clock. And they are at 11 with the heat in the Free State or wherever. There's no red spider mite over here anymore. They've all migrated down to where it is cooler. Now you're getting not even half doses. Totally underdosing late down here. And then a couple of days later, 5 days later, you call the contractor because the spray didn't work. You contact the supplier. The red spider mite is back. What's happening? It is because you're not getting good coverage. This one was an interlock trial that we did, top, middle, bottom. Still, you can see it going down, but the amount of coverage way better than without. Way better than without. So depth penetration is extremely important. Again, where is your target? Are you working with an upward, downward systemic contact product? Very important. Get that deep penetration coverage from the top to the bottom. Let me just check how we're doing on time. Oh, I think we're doing well. Probably about another 15 minutes, guys. Bear with me. This was a case study actually quite a few years ago. It was a potato farmer there up in the Limpopo in Petersburg. Aggravated phone call. Come and sort this out. I sprayed aphids and yeah, the chemistry doesn't work. Come and sort it out. Got there. The guy sprayed cyromazine, and yeah, there was definitely no control. Started working through the equipment, having a look at the equipment. The guy was quite aggravated. Nothing wrong with his equipment. He's doing the application himself always. You know how it goes. And yeah, he's got the sock applicator, the sock sprayer. The best there is with regard to coverage. All right. It's fine. Got him convinced to let's put out some water sensitive papers and let's go and have a look at the deposition. I've put off the sound because yeah, it was an aggravated farmer and he was speaking in single syllables. So I'm not going to share that with you. Just going to run quietly through this video. But we did put in water, run it over the potatoes. We had water sensitive papers on the top of the canopy, the middle of the canopy, and the bottom. And you would agree with me, how big can that difference be on that size of a plant? But interesting enough, we'll show you just now. So this was just water running up all the way to the top of the pivot there. At the top of the pivot, turned around, added interlock, mixed it up, came down, same just on the other side, obviously, with some new water sensitive papers, top of the canopy, bottom of the canopy, middle of the canopy, bottom of the canopy. And this was one of the papers. This was water going up. No issue spraying the top of the canopy. But what was quite significant, even on that height of a potato plant, there was a significant difference in the deposition that happened there. And it wasn't off-scatter. We placed this in the rows so that it had full exposure. There wasn't canopying or coverage between the top and the bottom leaves or in any way. I mean, it's obvious. You need to go and have a look at what's happening in the row, how deep it goes. And you can see excellent coverage on top. If this was a downward systemic product, no problem. But yeah, it is not downward systemic. It's upward systemic and contact. All right. At the top of the pivot, added the interlock, and this was a whole different picture. Whole different picture on the spray pattern, the deposition. Very interesting, very nice one. Yeah, to keep the business and the friendship. Yeah, we did help the guy out. This is one just outside of Bloemfontein, and the guy with his high boy sprayer, self-propelled sprayer. He was spraying a very expensive fungicide, ran around $700-800 a hectare for Alternaria and a couple of other things, pyroclostrobin and yeah, another thing in. I think you know what I'm alluding to, and yeah, he had problems controlling the infestation. So what we did, just had a normal water run going down. And water sensitive papers up in the top of the canopy and the bottom again. I'll show you just now. Just some. Let me just hang on. Let me run it. There we are. All right. So there goes the sprayer. In these rows, we've got the water sensitive papers packed out. This is water. I don't know what was previously in that sprayer. I wasn't too worried. It was an intern that I used to do the video. And there it goes. All right. Here in the foreground, let that by. Anyway, there you can, in the foreground, you can see the water sensitive paper. There it comes. Right on the top. And then further down in the canopy is another one. And you can already see the difference in coverage. All right. Collected then. This was the control. That was the top. That was on the bottom, top and the bottom. This was with interlock added, top, bottom, top, bottom. So do that comparisons with those and do this comparison with those. And you can see the difference, just another short visual. That's on the drift. Very obvious to see what's happening there. It's visually strong. You can see it. Right, I'm nearly done. We get sprayer systems that's got in this particular one that I'm going to show you now. It was Case Patriots with aim command on it. And one of the reasons why the guys put on aim command on the booms are not just for lower volume application, but for that droplet size regulation with a mechanical way to do it. It's these pulses for those of you that are not familiar with it. It's this pulsing of the spray coming out, generating a much more even spray pattern with regard to droplet size. This particular farmer there near Visualising, he farms around 12,000 hectares. And this was early days of introducing interlock into the market. So my colleague, Todd Cardwell, he's from Minnesota. Todd and I are good friends. He won't mind me saying this. He's pink like a Vienna coming out of Minnesota. And this was like early January in Visualising. So the farmer told us, all right, let's go and do it in the field. It was about 1 kilometer, 2 kilometers from the homestead. There was an open field that wasn't planted. And he said he wanted to see. Pulls up his 2 Patriots, which he was very proud of. And he said, all right, this is going to be the test. Add interlock on the one, and none on the other. He's satisfied on the calibration of both. And let's have a look. All right, I'm going to play this video a couple of times. The one on the left, control, that's like normal. And then the one on the right, we added to the system some interlock. All right, look through that spray pattern. And then look at this one. This guy over here, that's Todd. We nearly lost him because we were like an hour and a bit in the sun. But you can see that pulsing over there. You can see that pulsing. That's the aim command. And then obviously with the frame rate of the cell phone. But yeah, it's all not murky. I'm not sure what the English word is, but hazy. And a much clearer spray pattern there. Even look at the wet footprints here. Same volume. Look at there. Look at that wet footprint versus that wet footprint. So this is important. So what I'm saying, even with aim command, good nozzles, good sprayer equipment, and aim command, added technology like the aim command, you can still make the difference with a good adjuvant such as interlock. Now, this was just with water. This is going to be accentuated when you start mixing in different chemicals. We've shown a lot of things with water-sensitive paper. It definitely does help to paint a picture for us. The only thing with the water-sensitive paper is not always a true reflection of deposition. It shows you contact. A water droplet might hit that water-sensitive paper, bead up and roll off, bounce off, or whatever. But it will show up as a contact point, as a deposition point, but there might not be retention. So what we found was we needed another way to go and look at deposition and in particular retention on site. We've got a UV sensitive dye, one of these ultraviolet dyes that you can see under black light. Mix that into the systems. That's what we do these days. And when we do the calibration of the sprayers, run that over a target, and then have a look at how the deposition, and I want to say retention on the targets look like. Here you can see in daylight, we can't always wait for the night. We've got this spookhuis, not sure in English, haunted house, ghost gazebo is probably a better thing. The spookhuis. So during the demos on the farmer days, do the application, pick it up, get 4 guys, move it some anywhere in the field, drop it down in the field, go in with your black light, go and have a look. It's a quick look. That thing goes 45, 50 degrees Celsius very quickly in there. But it gives you the opportunity to go and have an assessment of how the retention on target looks like. Here on the right hand side, just a picture of some weeds that we did. On the next session, I will go deeper, pardon the pun, deeper into this and show you way down there a fungicide application. Point that I'm trying to make, we've got some new technology and new ways to determine how your retention on target looks like. Second last, our next webinars, which Dr. Brian de Villiers will present to us, is going to be all about that retention on target. Obviously also in the tank, but on target. What happens with your spray mix once it gets to that target? I've spoken on the journey there. We will cover what's happening on the target. There on the left-hand side, you saw that water just beading up, rolling off. In the middle one, non-ionic surfactant, spreader wetter. Everybody uses them. Breaks that surface tension, you get retention. But here on the right-hand side, you will see it looks different, that droplet. It's got more humectancy. That's keeping it that couple of minutes more moist in difficult circumstances, or if you have difficult surfaces on which you need to deposit chemistry, to really stay just that little bit longer moist for absorption to go in. Not just that. No, I'm not going to run away. I was starting to talk about waxy leaf layers and hairy surface areas. I'm going to leave that for Brian. Anyway, so teaser. Watch out. We're going to invite you guys for the next sessions very soon, probably in about 2 weeks' time. All right, last one. Take-home message on this. Control what you can control, starting with your equipment, right equipment selection, understanding what the capabilities and the parameters of operation is of your equipment. Chemistry does influence droplet size. Be mindful of that. Understand that. You need drift control. You need depth penetration. Leads to better deposition. And I should actually add and better retention. Adjuvants are not the orphans in the tank. They should never be the orphans in the tank. They are not the add-ons. A lot of our growers still believe the agent or the advisor selling an adjuvant, that is for his fishing trip or for his house by the coast. That is not the case. Every adjuvant has a particular purpose and function in some way. I wish I could give a one in all that does everything in the tank, in the air, and on the target. Unfortunately, it doesn't work like that. There are adjuvants that we need to add to the tank that only works in the tank. In the air, the very specific ones. On the target, very specific ones. All right. Please do understand, they are not orphan add-ons. And manage application risk with interlock. After you've done all the rest and understand the rest, you have a tool with solid data to show what the benefit is and how we can mitigate the risk. Anyway, guys, I once again want to apologize. This might seem very light, maybe repetitive to some of you that have already listened to this. But I hope it was insightful, or at least to start making a conversation so that we can go in deeper on this and have the discussion with your crop specialist. If I'm available or any of my other colleagues are available, I don't get out in the trenches as much as I would have liked to these days anymore. But I really hope that this can stimulate some conversation on good application going forward. Please, guys, drop maybe the questions for us via email. It'll give me an opportunity to really give insightful and in-depth answers to this. We can't, unfortunately, answer for everybody. So I do apologize for that. Thank you for your time, and hope to be able to see some of you guys very soon. Thank you.